Should the talk be in English or?
All right.
Okay.
Totally up to you. No,
If
no
it-
restrictions.
It's okay, in English. It's fine.
Okay. So great. Thank you all for coming. It's my pleasure to introduce today Francisco Cuevas, who's an assistant professor in the mathematics department of the Universidad Técnica Federico Santa Maria in Valparaíso. I always get confused with Piña. So.
Yeah.
And he obtained a mathematical engineering degree at the same university, also master's. He did a PhD in mathematics statistics at the Aalborg University of Denmark, and also has some industry experience at BCI.
Right.
So, yeah.
Okay, thank you for the introduction. This is a joint work that is now submitted for publication. So, discuss fingers. And this is a joint work with Gabriel Rico, who was my former master student when he done the coding, and Xavier Emery, who was helping me with all the data sets and interpretations. Gabriel is a student who did a lot of work here, and he's now doing a PhD in Germany. This is a work about a regularized estimation for highly multivariate spatial Gaussian random fields. And the objective of this work is to show how anonymization procedures are being used in the statistic data. So, what's the motivation about? So, first of all, we have a multivariate data. What does that mean? That we're observing plenty of different layers at the same time. And the thing is that for environmental science, this is something that is becoming each time more common. Yeah. So basically, you have a position and you are observing plenty of things at the same time, and you want to modeling them together. In the classical statistics bibliography literature, what they do is that they use maximum likelihood estimators. And if we want to jump into that theory, which is something that the statisticians really are looking for, they really want to have access to the maximum likelihood estimate because of their statistical properties. The maximum likelihood estimate cost, computationally speaking, is around n times p to the number 3. What does that mean? That n is the number of spatial locations and p is the number of covariates. So therefore, if I am increasing this number, then I increase everything by a cost of the power 3, right? Which means that it's very expensive to run the maximum likelihood estimate, right? So it means that then we have to run for some methods that can help me to optimize this thing, right? That could be efficient. So in order to deal with this thing, we will go first to figure out the problem. What is the old model I want to figure out? So the first thing is that in the standard literature, we will fit a covariance function model, right? A covariance function model is a function C. It depends on some parameters, theta, which is the one that we want to estimate, and this function should satisfy a condition, which is this condition here, which is called positive semi-defined, right? So a covariance function, when I evaluate it in different spatial locations, should satisfy this condition, and this means that often I have to impose constraints on where this theta parameter lives. Right? And this theta parameter now will live in this capital theta value.
How do you build sigma here?
Sigma is built by evaluating this guy in different spatial locations. And you have to.
C takes 2 inputs.
Yes, so it's C is having 2 inputs. Yeah, exactly. Or it could be 1, depends if you are assuming a spatial invariance, right? A translation invariance. So, yeah. So for the maximum likelihood estimate approach, what people are doing, and as I said before, is that you need to compute the determinant and the inverse of the covariance matrix. That's a problem of the maximum likelihood estimate. And the reason why this quantity are used is because they come from the Gaussian density. Yeah. So again, the objective function that I want to deal with is in the statistical theory, it's something like this. It's like it's a constant plus logarithm of the determinant of sigma theta plus the minus, yeah. And then you have an x minus vector here times sigma to the -1 theta and x minus, right? So what's the main issue here? That since we want to estimate theta here, which is involved into the sigma matrix, I need to compute the inverse. And this is the expensive part of the objective function for the maximum likelihood estimate. So the literature right now has been doing plenty of approaches for this, and we have the composite likelihood method, which was introduced by David Lacqua in 2016 for the spatial statistic context. And the Vicky approximations, that is something that was very old, but now people are using it a lot right now. Yeah. But neither A or neither B are addressing the problem when the number of parameters is increasing and when I have constraints into the parameters. And this is the main issue, right? Also, in plenty of applications, I need to incorporate the cross dependency. That is, one observation of one variable should depend with the other variable in another location. So that's why we are in this. So the advantage of this thing now is that we want to include sparsity. So the objective now is to take advantage of some techniques that we introduce sparsity to reduce the computational cost, right? So we will deal with a complete example where we have 36 variables and almost 4,000 locations, right? If I compute the full covariance matrix that is based on this in this case, right? It will cost around 130 euros, right? It's a lot. The classical computers, I still don't have that thing. I can do strategies, computational strategies, like write the matrix in a file or something, but it's very slow, right? So what do we want to do now is to introduce penalty in order to take advantage of the sparsity. And this is something that we can see a computational reduce a cost here, right? So the idea of the proposal here is to use some penalization in the objective function. So the idea is to propose a lasso penalty estimation, right? As I say. And this is basically you just wanted to use sparsity and mutualistic factor. All these things will be clear when I introduce now the model and so on. Yeah. We will use projected block coordinate descent, and then we will say how the parameters we choose the penalty parameter, and finally we'll see how this is impacting into the geochemical application, right? So if it's not clear what is the spatial data about, then we have here some covariates, right, that we are observing in some mining place, right? So we have, for instance, copper, ferrum, cobalt, and aluminum, right? All of them were observed in the same spatial location, right? These are 4 covariates that are among a list of 36 covariates, right? So I want to model them all at the same time. Why I want to do that? Because I want to explain, or I want to give a prediction how much of this quantity will appear in a location that I don't observe, basically. One of these points here, if I grab one location here, I want to see how much it costs to analyze it. It costs around $10,000, right? One point. It's very expensive data. So I really want to come out and say, like, in this location that you can observe, you have some quantity that is, so you really save a lot of money. So there's a money motivation as well, right? And in order to have an accurate prediction, it would be very nice if we can incorporate all the information that I have to predict and observe it, right? Therefore, I need to propose a model that can incorporate the relationships within the covariates. And second, I need to be able to estimate. This is the part that we are doing, right? So the main goal is to apply some technique called co-creating, which is a predictor based on different covariates at the same time, right? And using everything. Now, everything, we will see that it's not everything, it's almost everything. Yeah. Great. By the way, this has been obtained in the southern Ecuador, so it's not Chilean, unfortunately, but we can go there later. Yeah. So, the framework is the Gaussian, it's called the Gaussian random field. So when you have a Gaussian random field, it's a p-varied Gaussian random field. What does it mean? That jointly, this vector will have a Gaussian distribution, right? So I will have a likelihood function. And the covariance matrix, as I said, it's a field with this function, which we call the positive definite function, right? So remember that the matrix sigma should achieve a condition, right? Each time that I have this matrix sigma, I need to ensure the positively defined conditions. Yeah. This is the complicated part, right? A Gaussian distribution is identified by its mean and its covariance function. And since I observed p different covariates, this ij index are running from 1 to p, right? So this is speaking about how is the correlation between the random field itself together with what's the correlation between one random field, with I random field and j random field. That's how I can understand this matrix. Yeah. Okay, so classically, in one dimension, the people are often using this model, which is called the Matern model, introduced by non-Stein, but Stein has almost all the literature review about this. It was introduced by Matern. It's called the Matern because it was proposed in the thesis work from Matern in Sweden. He was studying some trees. And then Stein was using this to make the relationship with functional analysis about, well, this is the kernel for the solar space functions. And the thing is that, actually, if I compute the Fourier transform of these things, I will obtain the function 1 over 1 plus omega to the power alpha square to the power u. And this function is very relevant in spatial statistics because it has a parameter alpha who controls the range of interaction. And it has also a parameter nu who controls the smoothness of the realization of the random field, right? Why is the figures are important? Because the smoothness is saying something related to how different are the points when they are close, right? So speaking how much they vary, right? And yeah, there are plenty of connections with household dimensions or connections with smoothness and geometric properties around the realization of a random field, right? So there are some key properties here that they have a variance often. If I multiply this guy by sigma squared, like here, I will have a variance. There is an ergodic random field. It means that when I go far away between 2 points, then the correlation drops down to 0. The sample paths are of this, as I say, they have nu minus 1 differential. It's controlling the differentiability. And again, the practical range, which means that how far these things are correlated. So basically, I want to describe if this is differential or not, right? And also, I want to describe if I draw a point to match correlation, what exactly I wanted to do some inference about how big is this correlation about, right? To say these rocks are relevant to explain the other one at some specific rate, right? Now, this is one dimension, and it has some specific spatial cases like the exponential covariance function. It has only the one-time covariance function and so on. And that's why this model is relevant, because each time that I difference, each time that I move the new parameter, then there's a polynomial times the exponential, right? And when I go to infinity, then this converts to the Gaussian covariance function, right? Which is infinite with the outside differential, right? Okay, so with this function, since I defined it in one dimension, I want to jump to what's happening in the multiple dimensional case. And in 2010, he proposed the first related model. Right? And the proposal is easy. I had to make everything dependent on the random field that I observed, but it's not easy at the same time because if I impose these things, I have to be sure that the covariance function is indeed a positive defined function, right? And this is the complicated part. And that's why in 2010, he was dealing with this model, right? Besides of the constraints, in his paper, he was able to fit a covariance function model for three-dimensional random fields, right? So he's explaining three covariates at the same time. And the strategy to do that was easy. He used plugging into the solver, he crossed the fingers, and he obtained a result and say, this is satisfying the constraints. Perfect. Then later in Vanasovich in 2012, right? Vanasovich and Knighting, they were working together to make these constraints a little bit weaker, right? They relax the constraints, right? And in that context, what they do, it was to also put it in the solver. They propose, of course, more things, but they put it in the solver. They wait a little bit. They solve the result and say, okay, this is fitting well. It's satisfying the constraints. Therefore, I'm good. the main issue is that when you explore in these things, the iterations, what you are doing is making able to explore a space that is not feasible. So the method that they are using doesn't ensure that they will converge to something that is a positive defined matrix, right? And again, the other stuff is that they were able to jump up to a dimension 5. They don't go further because the computer will explode. That's the thing. So that's the first thing. And also, the other part important is that they impose some constraints on some parameterization parameters. Now depends on the marginals, and also they impose some. They add some terms here that they can somehow control how far do I have from the marginal average, right? So I have, let's say, random field 1 have a smoothness, random field 2 has another smoothness. I average them, and this term is controlling how far do I live from this smoothness in the cross correlation, right? So the model is becoming more flexible, but now I have to struggle with how to do this process. I mean, I really need to impose constraints now in the synthesization process. Yeah. So,
So is this like an if and only if, or it's just?
No, it's only it's like if this is a. If this is, I mean, if you impose this structure, the matrix will be positively defined. But it's not in the other way around. And there is a word by Emery, by the way, that he say like this can be relaxed even more. I mean, I can have
like higher order constraints.
Yes.
Okay. And all those constraints to actually be positive definite.
Yes, I can do a little bit bigger stuffs, and I can still have positive defined functions, but there is no characterization like this is an infinite function. This is the correct constraint. Right? It's complicated to do actually because everything is related to harmonic analysis. I have to go to the by the Wagner theorem. By the way, I have to prove that this is positive, and that's the complicated part.
And those relaxations are still always of. It looks like you're only looking at pairwise objects.
No, but yeah, these pairwise objects. Yeah.
So all these constraints are actually pairwise. Anyway,
but they are globally. This is for all the I and J.
No, of course, but you're not looking at higher order correlations.
No. They don't try to explore what's happening with the three stuff, and that's because in Gaussian process you need to see the pairwise. It's enough.
That's just my ignorance about the multivariate. Do you have the same regularity chance that you have for the one-dimensional?
Sorry, you have the same
regularity chance that if you have 10, for example, so the condition you get in a somewhere space realizations.
Yeah, that's something that they do in the diagonals. Let's say if I have the marginal in one random field, I have this property, but in multivariate setup,
specific direction.
Yes.
Okay. Yeah.
So yeah, it's that's really it's something very hard to prove these things. And then the work after this one in 2019, I think, or 20 from Lee, he goes with a little bit more flexible constraints. Right? So they are flexibilizing the model a little bit more as well. Yeah. But it really needs to do a lot of heavy stuff about the harmonic analysis. It's not easy. Yeah. So the thing is that then each condition is controlling different aspects of the gross covariance function. As you say, this one is controlling the smoothness between the cross smoothness, which whatever it means, it's not easy to explain. But what is important is also the cross range practical range, right? And this model is controlling the cross practical range via this term here, right? Okay, so the important thing is now we have a model, right? And the thing is that if we put these parameterizations into the model, then if we impose these things, then we will have a model and we will have also a parametric space that we have to control, right? Basically. Yeah. So we call this the Apanasovich. When we impose these things and these constraints here and we plug them into the model, we will call this the Apanasovich parameterization because it's the one that we will model, right? So basically, we are parameterizing the cross products, the cross terms, and we are writing it in terms of the diagonals. So that's the question. Yeah. And we will add the deviation via a matrix R, which are correlation matrices, right? So we are now having a way to control the deviations, how different is from the average of the cross random things. So with all these things, then the strategy now is that we have this term, which is the covariance amplitude of and the constraint, and then we have this model, and this is the model that we have to use. So this is the model that we want to estimate. Okay. Look at the number of parameters I have. It's a little bit big, right? It's a lot of parameters. And as I say, in the V15 case, they deal with 30, and it's just plug it into the solver. And yeah. So there is a situation related to something called identifiability. What does it mean, identifiability? That I want to understand that if I have a set of parameters, then the model is unique, right? And it turns out that if this term delta V is equal to 0, then I cannot estimate this matrix because I can plug whatever matrix I want, satisfying the constraint, and the model will be the same. It doesn't change, right? So this is something that I have to take into account when I do the estimation, because this term is somehow saying how do I delete. So what we will do here is just to redefine this term and write it like this delta parameter. We will estimate everything at the same time, right? So with this parameterization proposed by Apanasovich, then we will solve this identifiability problem, right? And something else that we will assume in this work particularly is that we will assume that the smoothness is constant, and the reason it will come later, right? Because it's basically complicated to find a predictor, right? So the strategy, as I say, to estimate the parameters are basically plug them into the maximum likelihood estimate. As I say, this is the complicated term. Oh, there is a minus. Yeah. There are minus. It's just I. But the thing is that I have this term, which is the determinant, and then I have this inverse matrix, are feasible for large. And what we will do is to propose a composite likelihood approach. What is this composite likelihood about? You split the likelihood here. Instead to compute it with the whole vector, you will compute the likelihood per pairs. So you will establish what is a pair about, and then you compute that likelihood with the two pairs, and then you will repeat it among all the pairs following a rule, right? You multiply by this weight here, and this weight is a binary value. So you have a weight could either 1 or either 0, right? Since we have this weight, then we can relate it to the spatial distribution. So the thing is, if I choose this weight smartly, then I will save a lot of computations, right? Because then I'm saying here basically that I don't need all the pairs to estimate the model. So the most important proposal now is to fix a number of neighbors and use Scanner's neighbors, and then in that type of pairs, I will compute this very well. So what's the advantage of this thing? If I compute the log density, which is basically this term, but in two pairs of vectors, I'm reducing the computation from p times n squared to whatever the length of the vector is, right? And in this context, what we will do is to graph one spatial location, another spatial location, all the covariates together, and we'll compute the likelihood. So we're reducing these two times 2p times 2p matrices, right? So we're reducing now the inverse of this big matrix, which is n, is the p n squared, 2p times 2p. That's the first thing, and this is how do we get a lot of speed, right? So remember that the dimensions of sigma is a is a n times p times n times p, right? This is the dimension, and we are reducing now to a 2 times, right? And this reduction is right? And then we have to complete this. Primitive times, depending on how many nearest neighbors do I have per point, right? So if I fix 5, then it's n times 5, and some is 5 fast, right? So then I'm reducing a lot in memory and also in operations. So then the proposal was to use a lasso estimate, and the reason why lasso is relevant because it will introduce sparsity in our estimation. Yep. So I will add a L1 norm, and I will give a penalty in the Cholesky factor or of the covariance function. So what's the thing here that I think about? That this matrix then could be written basically as a matrix of covariance, a Kronecker product with another matrix equal M, and this matrix had the information about this will be a small covariance matrix, which is basically a covariance matrix that contains the information of if random field A Y is correlated with random field T, right? So this is a P times P matrix. And I will add a lasso penalty here because if I plug a zero, it means that I have plenty of zeros in this product, right? So I will put a penalty in this term, right? And that's why this is important. And the reason why I want this model also is because it will help me to recognize which random field is correlated with another random field, right?
I got confused because I don't clearly see how theta is impacting sigma, or the sparsity of theta is impacting.
Oh, this one?
Yes.
Yeah, because
That-
if
Was that follow from the previous characterization or
from here?
no,
Because-
even earlier? When you had this
Yeah,
theory about.
it's from this characterization here.
Okay.
So the thing is that if I add a zero here, right, then I have a plenty of zeros in this coordinate. That's right. And the trick is that I will grab this term and I will put it aside, and this is basically a Kronecker product times another matrix.
Okay, but the parameters theta then are related to the sigma.
Yeah. So with that thing, then if I penalize that part, then I will save also a lot in computations because I have to then believe I will have a lot of terms that I will not solve. Right? So then we will penalize all the terms that are off of the diagonal, right? And this is something that will ensure positively defined if I am in the parameter space, right? Now, how do I ensure that this will be parameter space? And this is the main part, right? If I stick to the parsimonious version of the model, which means that I fix the smoothness, then I have to estimate all the sigma squared, alpha, delta, L, or an R, right? And L is what I call here psi, yeah? And I will find that each term is leading on all these spaces. So I have plenty of, it's a product space. So I have RP, where sigma squared lead. I can write an RP because I can parameterize in such a way that this will be only a term that lives on RP. It means that I can explain this as an exponential of something. I have alpha, which is a vector of also terms that should be strictly positive, but if I parameterize this term into exponential of, right? And if I write this, I have sigma squared, but I can write this as exponential of S, and also I have alpha, which I can write as exponential of tau, right? Then I have terms that and then I can perform the minimization of RS and tau, and this leaning on RP, no problem. Delta B will be a strictly positive term. We didn't parameterize this one because we are interested on see if this is zero or not. And L, it's a tridiagonal matrix, right? So it's a lower triangular matrix with positive terms in the diagonal. And RB, it's a matrix which should be conditional negative semi-defined, right? Which means that it's more or less like negative. It's like the minus a positive semi-defined matrix, right? Plus a constraint on the liaison.
Conditionally, what?
It's called conditionally semi-defined. It's this basically. Conditional negative semi-defined is basically a matrix that is minus semi-defined, but I have to sum one in the. That's basically. Yeah. So the thing is that all these spaces are convex, basically. And now, if I look at this thing, then I can estimate everything, not independently, but I can then use and take advantage of projected gradient methods. Right? And this is where I'm going. Well, I have this conditional semi-defined function. So what's the method about? I think that this is something that in this audience I don't have to explain that much, right? But basically it's just run the gradient method as we know, but each time we are updating one part of the block and then we reveal it. Yeah. And what I have to do is to have a learning rate or a token problem. And I have to be able to compute the gradient of the objective function. And as I say, I have to update all the vectors except this part, right? And no, sorry, this part of the vector fixing the rest. As I say, the vector parameter vector is divided into this, and then I have to reveal it. And each time that I do the gradient step, I have to project it into the space where this theta one is leading. right? And the good thing is that since all the spaces that I'm using are convex, then I have the projections. I can compute them. And if I cannot compute them explicitly, I can do a numerical approximations of them, right? So this is the good part. Yeah. So basically, for instance, for the lasso updates, then we have this maximum, this soft thresholding operator. So it's how it works. So then the algorithm is summarized as follows. We have then an estimate of diagonal terms, and that's a good thing, that the marginal terms of in this case of the diagonal terms, that means that the random field of the random field by itself can be updated just marginally, because I'm updating only just that part, so I can use them as a starting value. I don't have to update them anymore. So I estimate the marginals, and then what I will do is update only these terms, right? And that's the advantage of this part. And now what I will do is just repeat this thing until get convergence, right? So I update L, I project the update, right? Then I reveal the matrix, and then I project delta, and then I project R, and so on, and I reveal until get some convergence, right? Don't ask me why this convergence. Yeah. The good thing of this is that if I believe in the convergence, each step that I'm doing is inside the parametric space. And that's the positive part of this method, right? That all the iterations are part of the feasible set. So I will get always a positive final matrix, right? So in order to do this, and since we're doing a lasso estimate as well, it's often complicated to propose a starting value for the lambda, which is the penalty term. And also it's very important because it really will say what's the quality of the estimate. So we'll start from something that is ensuring that everything is zero. And then I will make this lambda decrease up to get some grid search, right? So what I will do now is to grab this lambda such that everything is zero, as I say, and I will multiply by 10 to the power minus 8 because it's what the regularity say, basically. It's what the people are doing in this context, right? And then in order to choose what is the best lambda, what we do in this context in statistics is that we use either the Gaige information criterion, which is given by this quantity, but since we will use composite likelihood, right, we need something similar. And this is the proposal of Monet and others, where they want something called CLIP, which is composite likelihood information criteria. And it's something close similar. It's this, the composite likelihood function minus the trace of this matrix here, which is related to the variance of the parameter, right, estimated parameters. Right? The main issue of this thing is that all these estimates, right, now that I can compute some theta and I get some estimate, right, and I can run the performance of all these things, I will not have access to this guy directly, right, because of the theory, it doesn't allow me to do it. So what I have to do then is estimate this guy by subsampler. And this is something I will discuss later, right, because we have to perform some bootstrap estimates, right? So as a matter of example, to see how do this works, we will start with p equal 5 and n equal 500. The reason why these numbers is just I have to run a simulation, right? There's nothing behind. But the good thing is that I can perform simulations in a computer, right? Exact simulations on the computer, and also I can control this. And we simulate from the Matern model, really, real model. So we have some parameters here, and we have some correlation structure, which is depicted in these figures. So what I can see is how the correlation looks like in the diagonal, right, which is the Matern covariance function. But out of the diagonal, I have some cross correlations that are also a part of this model. So the good thing is that the correlations outside the diagonal are not necessarily zero, right? And he will deliberately put some correlations that are 0.5 outside the diagonal, in the diagonal 1, which means that here, where I have correlation, and outside it could be zero, right? It's anything. So this is one realization of this guy, right? So these terms are not necessarily correlated, but they will have some expressions, right? So This is how a realization of the Gaussian random field looks like, right? So we have set 1, set 2, set 3, set 4, set 5. And since 1 is correlated with 2, and 2 is correlated with 3, and 3 with 4, and 4 with 5, and that's rate of 0.5, we will see some similarities. But we have to understand also that set 1 is somehow correlated with set 3 via set 2, right? So that's the wonderful of the model, right? So this is an example of how the model looks like, and what we want to do now is try how this estimate works. And what we'll do now is to compute a lasso for this one simulation. So it's just to see how this works. What is the workflow allowed if someone wants to estimate the model using this method? So the thing is that then I will have a solution path, which is the proposal of lambda and going down, going back. And this is the percentage of zeros that I obtained in the correlation matrix, right? It's around 30%, right? And the red one is the real value, right? And here is also around a 40%, right? Which is something what I do when I compute in the correlation in the what's it called? This is in the Cholesky factor, and this is in the correlation matrix. I mean, when I recover it from the zero when it's sparse matrix. And this part here is basically saying how this path, solution path is changing. The red line here is the true value, and it's also the selected value, right? So we have all these features that are very quite common into the lasso bibliography, like the coefficients start from 0, and then you are getting something 0. And the thing is that when you are going close to 0, this estimate is becoming very similar to the non-penalized stuff, which could be the line, right? So in this context, we are using the maximum value. This is something I say. So what if we do concreting with these random fields, right? And we have set 1, set 3, 4, and 5. So this is how, remember that we are having this, let's say, set 3, right? And we were doing concreting it to set 3, and it's recovering plenty of the features, right? So you have plenty of red here, it's filling with these, right? So it's basically close similar. And we are doing this concreting estimate with the Gaussian index. So we are selecting lambda with using the Gaussian index, right? And we can find that this is a minimum for this stuff. So it's selecting them, right? Okay, this is a lab example. And also what we have here is how this method is identify the zeros. Now, the thing here is that what I'm doing to compare, right? This is the correct zero positions in the L, and this is the correct zeros in the likelihood. So I'm comparing what if I change the objective function, right? So in the case of the likelihood, and in the case of the composite likelihood, they are close similar identification, right? So they are really identifying what's going on. So now for the composite likelihood, I have a little bit of bias, right? But the reason is, well, I will explain the reason later, but in the case of the likelihood, this is identifying very well what are the points of, right? What are the relevant rates? Yeah. Now, for the estimation procedure, we also are interested on the time, how the time is changing, but depending on the objective function that I'm using. And we can see here the effect of the change from the likelihood to the composite likelihood. And we can see that the likelihood is at the beginning with N100 and 5 random fields. This is jumping from 0.61 minutes, 5.6, and then 500. I mean, it's really exploding. But if I go to the composite likelihood, I can see that this is also increasing in time, but it's more reasonable. Right? And I'm reducing this in a factor of 100, so it's a huge saving of time, right?
This is N is the special, the number of
special parameters. Yes, I can't change the
number of fields.
Yeah.
The number of fields is the same.
Yeah, it's fixed. The number of fields is fixed, but the number of spatial coordinates is changing. Yeah. Now,
but this is the time that you use using your regularization.
Yes. It's using the. I mean, it's you can fix one lambda and wait until this converges. Yeah. So this is the computation there. So when we also had the same. I mean, we did also the same experiment for a little bit more random fields. We jump until 7 because then the computer can't simulate yet, right? And we see we don't see differences in the growing end. And with the random fields, of course, we have some difference. It's not so meaningful. Right? So now we jump to the data set. So this is the data set location, right? This is the spatial coordinates. And this is, again, in each coordinate, we are observing 36 variables, right? Well, we have 9 major elements and 27 trace elements, right? And we have almost 4,000 spatial locations, and this is this is the spacing of these things: 5,500 meters and 6,500 meters, right? North south, and 5,500 east west, right? The elevation is around this one. So now we will assume that this data is in the plane. So forget about the surface and the elevations, right? Because I want to see what is the method showing me, right? One thing is that these covariates often are written in percentage. So the bibliography is saying is that you have to transfer into the normal scores and you do statistics there. So I will not question that thing for now, right? But what we can see is what is the random field composed about, and we can estimate the nugget seal ratio to see how much noise do I have. And we can see that the ferron is the covariate with more noise than the others, respect to the others, then aluminum, and then Cooper, and then, cobalt, and then Cooper, right? And what we will do is fix this the smoothness to 0.5. It means that I will assume non-smoothness onto the Gaussian random field. This could be something that people can question, but I can always do this, right? And for the gross covariant terms, we didn't identify a nugget, right, yet. That's also complicated stuff. We will assume that there is no nugget. The nugget is basically a noise in the diagonal. So it's some noise. So you assume that the noise is only in the diagonal of the random field, but there's no cross noise. That's the right. Well, these are the random fields that I'm analyzing, right? So the non-smoothness hypothesis is reasonable. Now, how much non-smoothness? That's something that people can question, but when non-smoothness will be fine, right? So now we'll jump to them and this is what we want to do is to perform concrete, right? We want to predict in a non-observed location. Right? The cross covariance, the cross variograms that we observe also to have some input about how is the correlation between these two things looks like this, right? And these are the results, right? If I run these things, we can see how are the sample paths, right? The trace respect to lambda. As we can see, the ferrule in this context, when we select, first I'm using composite likelihood because likelihood wasn't able to finish. I mean, the amount of memory that I needed was too much. The method didn't even start, right? It's stopping to the filling of the covariance matrix. But when I jumped to composite likelihood, the method was able to finish, right? It took around 6 hours to finish for all the solutions that I have here. So if I run it 6 hours and I have all these plots, right, all the trace plots. So it means that I'm solving things 7 times. And I'm using warm starts. That means that I use the previous solution when I update the lambda. Right? So what we have here is that the ferrule, it's really selecting no covariate to explain it. That is because of the high level of noise. Right? So the high level of noise is somehow disturbing the selection. But when we go to the Hoover, which is the covariate, which doesn't have so much noise, we can see that there are some covariates that are meaningful to explain Hoover, right? So that's the objective of this method, is to identify which random fields are useful to propose a prediction, right? Regarding the number of zeros in the covariance matrix, we can see that respect to the lambda, right? We can see that it's selecting around 85%, is 89% of zeros, right? It means that it's giving a very sparse matrix, right, in the covariance. So it says that this random field, not so many random fields are interacting with each other. Right? That's a good thing. That's a good thing, right? And when we see the psi matrix, which is this is the psi matrix, we see that this is happening, right? So it's then it switched to 52, right? So it says that half of the matrix is filled with zeros, and that means that I can really do clusters of which covariates is belonging to the other, right? And if I plot the criterion here, it's a lambda criterion. It's really it really helps because it's really identifying. Now, to compute that thing, I have to split the data into a test training data and into a test data, right? And then I do prediction on the click, right, and model, and then we perform these performance metrics, and then we can see that the mean square error is around 0.7, 0.8, 0.7, and so on, which is like something that is leading how much error do I have. It's not so meaningful right now, but it's basically saying that the method is not working that bad, right? It's a reasonable fit. And finally, the number of variables that I have to use on each one of selected per lambda, right? And the time that was used to compute for clicking, right? It's shown here, which means that I'm running from an error from 0.7345 to 0.73, 0.9, which means that the method is really selecting the covariates that are relevant to explain. If I want to go down to 4 covariates, I have a very tiny improvement. And in the standard deviation, this is going quite nice. But as you see, the time that I need to compute the predictor is really reduced a lot. I mean, I really save time if I want to give some reasonable performance. And this is by choosing the probability lambda, right? So as a conclusion, then we have a lasso penalized estimation framework, right? So we are introducing the penalty complexity factor, and well, we are doing the selection of lambda via tailored criteria. And the good thing is that now we have a method that can feasibly estimate the Gaussian random fields in a multivariate setup. The limitations of these methods are the smooths, right? Of course. The lasso, which is somehow something that I use a constant, a fixed value of lambda. I'm not using other lasso penalties, right? So this could be something that people can say. Or also, studies like adaptive lasso, like can be explored as well. The theory can be extended to this thing. And the selection of the weights of the composite latitude. Right now, we fix a number of neighbors as 5, but that's something that we didn't explore that much. It could be 7, it could be whatever, right? So I don't know. And yes, to explore this into other models, right, like non-stationary models and so on. So that's all done. Right? This is the phasing bibliography, and that's all.
Thanks a lot, Francisco, for any further questions. Here.
Thank you very much for the talk. Let me ask maybe the student questions as a complete foreigner to the topic.
Please.
I'm surprised about the difficulty of computing the log estimator. So my first attempt would be to try to approach this as a complete optimization problem. So I'm wondering what has been done there. Like maybe do this in a gradient-free setting or in a quasi-Newton setting where I can approximate the gradient. Like how far did optimization go about all the statistical considerations for this?
Yeah, that's a good thing. Well, the classical minimization procedure for this is use the basic thing that you will do as a statistician is just put the likelihood and put it in the team solver and then cross fingers, and then people do this. And of course, there are techniques like derivative free or, for instance, BFDS, right? Techniques that you can use. But the idea of compute the gradients and so on is something that is not so popular here. And basically, because of the objective function here, this term, here, basically because that term is quite expensive, right? So what are people doing here to deal with this? Well, there are plenty of other strategies. This is fine, right? You can also use tapering, right? Which means that you are multiplying by a covariance function that is 0 at some point, right? So you impose sparsity by multiplying by Earth function, right? or there are techniques like take advantage of the spatial structure and use Fourier transform to complete the inverse. So at the end, it's not the minimization at all. The problem in this function, it's the storage of the covariance matrix, right? And in that way, there are plenty of strategies.
Okay.
So any strategy I will set in memory will be very welcome. The something that I saw also is the technique of hierarchical matrices. Yeah, there are a lot of people. There are some people doing this, but the problem with the hierarchical matrices is that the doesn't ensure that this is positively defined, and this is the issue.
You mean the inverse or?
Yeah, for the sigma matrix, or well, the inverse. I don't know how it works really, but I saw some works that they are doing hierarchical matrices. Yeah, they have issues with the possibility definedness of the matrix.
I would think, for example, in a sparse approximation, there's this sparse approximation inverse technique, specifically generating an approximation of the inverse. I guess it's without computing.
Yeah, indeed. That type of techniques, like a Bragg matrix here, which is already sparse and blue iterations, are also used. And they say instead to estimate sigma, let's use the inverse, right? And then you change the matrix and do a statistic. That's another approach. And that approach is more related to another type of data, which is it's called the AL data. Basically, you're interested in the connections between the neighbors rather than the spatial structure of the covariance, right? So yeah, but that's another approach. And the connection is with the partial differential equations. There is a deep connection between the sigma matrix and the heat equation and the final element methods. There's a lot of things to learn.
Thank you. Other questions?
So I have one.
Yeah.
It's about the optimization algorithm.
Yeah.
And specifically, right? So I'm just curious about, because I couldn't keep track of everything. You're doing the coordinate descent stuff, and then you're doing a couple of projections, right?
Yes.
I'm just wondering, those projections are to PSD cones, right? Like there's a positive semi-definite.
Yeah.
Right?
Yeah.
So what's the dimension of those here? Like
of these matrices?
No, of the positive semi-definite cone you're projecting onto.
You mean?
I mean, I think it's that PCD.
Yeah. This one. Yeah. Okay,
right.
This one. No, the dimension of this guy is not so big actually, because it's this R matrix here is a P times P dimension matrix.
Okay.
It's tiny. Yeah.
Okay.
It's tiny with respect to
many of them, or
no, it's only one.
Only one.
It's only one for the whole problem. Yeah. So it's really a huge reduction.
All these things are operating on P or P squared variables.
Exactly.
That's the coordinate descent and the projection.
Yeah. That's the advantage here. Yeah.
Okay. Great. Yeah. Thanks.
So you mentioned the smoothness parameter, so it's related to Sobolev smooth.
Yes.
So it's basically when you choose one half, this would be like H1 half smoothness.
Yeah, it's something like that. Yeah. I'm not so familiar with the connection, but I know that when you define Sobolev space via for the transform, then you have this 1/1 plus W to a square power alpha half, plus the dimension. So the thing is that there is a connection between the random field that you observe and the Sobolev space where it belongs to realization. Yeah.
So is there so you choose one half just because?
Oh yeah, because
it's just why not 0.6?
Yeah, that's a good thing. I mean, that's a good point. It's like when you see this random field, it's like okay, it's not smooth, so it should be less than 1.
No, but I see that it's one half, right?
Yeah. You see, okay, it's less than 1, but it could not be 0.2, or maybe yes. Actually, my Emery told me, look at CSA, it should be 0.235. I was like, why? Because it seems like that. Sorry, I fit 0.5.
There's no smoothness test you can do on the data.
This one is not smooth.
No, I mean like is there like a smoothness test you could do? Like if you have a guess,
no, actually, the theory of random fields, that's a good point. I mean, I didn't want to deal with the smoothness at all, because in the random field theory, you can prove that the statistical properties of the parameter estimates, when you don't fix it, there is something called the microergodic parameter. So you cannot estimate it from the data alone. You have to estimate the ratio. Actually, in one dimension, what people prove is that what you can estimate is not nu. What you have to do is estimate this over this to the power is this to this. No, sorry, it's something like this. That quantity you can estimate it. If you fix this one, then you can estimate this ratio somehow, but you cannot estimate the nu by itself. So what people are doing is they fix this, and then you can estimate this on this. Right? So this is it's something called the microergodic parameter. So that's why people often fix it and forgot about it. But yeah, find a good estimate for this parameter is something as a research study actually today. Yeah, and it's related to fractal dimensions and to how is it called, to smoothness of some parameters. So it's not easy. When it's less than 1, you can use box counting to have an estimate. Yeah, that's what we do. And when it's greater than 1, people don't go farther because you cannot distinguish what is 1's time derivative with respect to 2 times derivative because it's discrete data. So they keep until 1 and then you break. Yeah.
Questions? Okay, so Francisco will be at the IMC for the afternoon if you want to have any further questions, but